Hello, good morning all. Happy Independence Day. Today in this lecture, we are going to start with the eigenvalues and eigenvectors pertaining to some special matrices. And as we did yesterday, we did till I think unit we actually found some results for the eigenvalues of the Hermitian matrices. Then we found some results on eigenvalues of symmetric matrices. Okay, we also wrote some results regarding eigenvalues of idempotent matrix and nilpotent matrix. Today we are going to continue a little bit further on this topic only. Okay, on this topic only we are going to go a little bit further. Okay, okay, so this is what we did yesterday. A little bit of that, and then we'll move forward. Okay, so I hope everybody has joined. I'll start once everybody joins in. Okay. So yesterday we were doing all sort of different topics. Today also we are going to continue with the same. We did eigenvalues, eigenvectors of some special matrices that as I told. Today let us begin with eigenvalues and eigenvectors of one of the matrices that actually was left pending. So yesterday I taught you about special matrices and eigenvalues like Hermitian matrices. I also drew a parallel between Hermitian matrices and symmetric matrices, and I told you that if the eigenvalues of Hermitian matrices are real, so the same result would apply to the symmetric matrices. For symmetric matrices, we developed one other relation that for a symmetric matrix, we can always choose a eigenvector that is completely real. That was a special result for your, you can say, uh, for your symmetric matrices. Now let us today discuss the eigenvalues of let us today discuss the eigenvalues of eigenvalues of skew symmetric matrix. Skew symmetric matrix. So what do you think the eigenvalues of skew symmetric matrix would be? So what is a skew symmetric matrix? We all know that a skew symmetric matrix is given by if if A is a matrix which is skew symmetric, then I can write that A transpose would be equals to minus of A. If this is the case, then we say that our matrix A is a skew symmetric matrix, right? So this is what we say. This is what we say. Okay, skew symmetric. Now, what the eigenvalues of skew symmetric matrix is? I'm going to write the result. They are either 0 or purely imaginary. Either they are 0 or they are purely imaginary. This is one of the important results. Okay, and most often you will find that if you remember these results, even if you don't know the proof, that things would be fine. So for example, I would like to prove it, a little bit of it. Okay, so a little bit of it I'll prove. So I know that my A is a skew symmetric matrix, that implies A transpose is equals to minus of A, right? A transpose is equal to minus of A. So A transpose is equal to minus of A. Now, if X is an eigenvector, then I can write AX is equals to lambda X. Okay, and if I multiply both sides by X, you can say X conjugate transpose. If I multiply on both sides by X conjugate transpose, what do I get? I get X conjugate transpose, A transpose, and then you have this X, and then you have this lambda, and then you have this X transpose, and then you have this X, right? yesterday also I told you that if let's say this is your x, and if I take a conjugate of it and transpose of it and then multiply it, x conjugate transpose x, this is always greater than 0 because this represents the length of the vector. This represents the length of the vector, that you can clearly see. If we do this way, it will come out as x1 conjugate, x2 conjugate, and then it is multiplied with x1 and x2, like column vector. So you will get x1 square plus x2 square, and this represents the length of the, its root represents the length of the vector. Okay, so its root is nothing but it is equals to x transpose dagger, x transpose x conjugate transpose into x, and this is at times also referred to as your norm. Okay, so this is at times referred to as your norm of the vector also. Okay, so these are the few things that I wanted to tell you. Now you see, if I multiply both sides by x transpose x conjugate transpose on both sides, what will happen? Okay, what will happen? So why I have taken it in general? Why I have taken it in general, because then this will also make a result for skew Hermitian matrix also. So that is why I have taken in general. Okay, in general means I have taken a conjugate and then transpose as well. Okay, if it is real, then conjugate does not make any sense. Okay, okay. So always remember this. We are going to little bit learn in quantum mechanics also, and this is very important. This is in the language of linear algebra is called as the inner product, or you can say simply dot product. Okay, now you just see that dot product is commutative. Dot product is commutative. So what I can do on the left side, so I'll write it equation number 1 here. Achha, okay, this is something that I can do. X transpose A transpose X is equals to, I can write it as, okay, sorry, this is norm. Okay, so this is equals to lambda norm of x square. So this is how you write it. So this is equivalent to writing this. Okay, I hope this is clear to you. Now you see this. Let's say this is equation number 1, and now just think about this equation number 1, the left side. Just think about the left hand side. So I'm just concentrating on the left hand side of equation 1. So if you just concentrate on left hand side of equation 1, what you are getting? We are getting x conjugate transpose A x, and this particular thing you can write it as what? You can write it as A x transpose, because A x transpose would be x transpose A transpose, and here it is x conjugate, and it is equivalent to what? It is equivalent to writing. Okay, you can think of this way now. Is that clear or not clear? See, I told you now, keep the inner product or dot product. See, what will come out of this? So you just remember right now that this is inner product and this is dot product, and dot product always remain. You can say that it always remains commutative, so that you will be able to understand what I want to say. It always remains commutative. So I can write this way. I'm writing it here so that you don't get confused. See, it implies what? So it implies that this particular thing that is written over here can be written as, it can be written as what? It can be written as, it can be written as product of x transpose and ax. It can be written as the product of x transpose means x conjugate into ax. Okay, now you see this particular portion. Just think about this particular portion. If I want to write this particular portion, what it will come out as? I know that x transpose ax can be written as ax, and then I can have this. What I have done, I know that if see here I can say. I think you are not aware with the inner product spaces now. So what should I do? So I want to say that if I do this AB, okay, whether do I do this AB or whether do I do BA, it is one and the same thing. First thing that you should understand, when I say that the dot, here I'm writing, if I want to say that my dot product is commutative, it implies whether I do AB or whether I do BA, it is one and the same. Dot product is commutative. This is what I want to say. Dot product is commutative. So if I do B, so here just think of it, this X conjugate transpose. So if I write X conjugate transpose AX, okay, this is same as writing AX conjugate, and this goes there. This is what I want to say. Since I'm writing, since dot product is commutative. I think similar treatment you might have seen in your quantum mechanics. If you have not seen, then please remember this, because actually I thought that inner product spaces you know, but even if you don't know, just think this as dot product. So this is A, this is B. Okay, so if you know now, for example, when I say cat and bra notation, okay, so let's say you don't know it. Okay, so let us say that dot product is commutative. If I say A dot B, it is equivalent to B dot A, and if I'm writing A as X conjugate transpose B as AX, then I can write it as, if I'm writing it here, it implies AX transpose, and I'm writing it there. So basically it is BA. Is that clear? So I can write this way. I hope it is clear. Or should I repeat all the statement all over again? Okay, so I hope people have got it or not got it. I don't know. So I'm waiting for the response. Okay, good enough. So basically what I have done, I have used the commutativity of the dot product. Now what I can do is, now this particular portion, so just focus on this particular portion. I know this can be written as X transpose, A transpose, and X simply. And I know that since matrix is skew-symmetric, I can write this as minus of A, right? So I'm going to write it as minus of A. I hope it is still not clear. And this particular thing, I can write it as what? I can write it as, I think this is what? I think AX, I'll take an, this particular thing is what? It is equal to what? So AX, here you're getting AX, right? Okay, no, here it was bar, I guess. Here it was bar. Okay, so it is X transpose. I'll take a negative common out. So I'll get minus of X transpose A, and then X conjugate. Okay, so just think about this. I know that my matrix is skew-symmetric, so my A transpose would become minus of A. Here it is, and this negative I'm taking common out. Okay, now just think about this. Okay, so this is your left hand side. I will write, this is your, I'll just write it here so that you don't get confused. This is your left hand side of equation number 1. Okay, this is left hand side of your equation number 1. Now just think about a few other things. For example, let's say I'm saying that if AX is equal to lambda X, okay, if X is equal to lambda X, then what I can do, because I don't know about this, then what I'll do, I'll take a conjugate on both sides. I take a conjugate on both sides. What I'll get lambda bar, and here I'll get X bar. Okay, this is clear. And if this is the case, on the left hand side of if I multiply it with X transpose, okay, if I multiply with X transpose, so minus of X transpose, if I multiply on both sides, what I'll get this, and this is equals to lambda bar. Here I will get X transpose, sorry, and then X bar, right? Is that clear? Is that clear or not clear? Please let me know. See, what I wanted to convey was, this was your left. See, again, come again. Just think of it, what I'm doing. See, I'm discussing about the eigenvalues of skew-symmetric matrices. A skew-symmetric matrix is what? It is equals to A transpose is equal to minus of A. And I'm doing it in general. Let's say I'm not talking for the real entries. I'm talking in general. Okay, so what I will do, I'm claiming that these eigenvalues are either 0 or purely real. So how would I claim it? I know that a skew-symmetric matrix is one where A transpose is equal to minus of A, right? Or in general, it satisfies the equation AX is equal to lambda X. Okay, now what I would do, I would multiply both sides by X transpose. So I have multiplied X conjugate transpose. This is X conjugate transpose into A transpose into X is equal to lambda X transpose, lambda into, I think I should have written here, X conjugate transpose. So this should be X conjugate transpose. Okay. So if I take a X conjugate transpose into X, what do I get? If I take a X conjugate transpose, so I taught you that X conjugate transpose into X gives you a norm square. So this is what is equals to the lambda norm square. So what I would get from here, I'm just concentrating on the left hand side. So if I concentrate on the left hand side and use the applicability of the dot product being commutative, what I can say that this particular thing, if I write X conjugate transpose AX, I can write it as AX transpose X conjugate. So basically I'm using the commutativity of the dot product. Now I know that AX transpose is what? It is equals to X transpose A transpose X conjugate. And here what I can write, I know that my matrix is Q symmetric, so A transpose would be minus of A. So I take a minus outside, I'll get X transpose A X bar, A X conjugate. Now I'm thinking about this. What is this? I know that my AX would be equals to what? My AX would be equals to lambda X. Now if I take conjugate on both sides, so what am I getting? I'm simply getting AX conjugate, lambda conjugate, and X bar. X, or you can say X conjugate, right? Now if I multiply on both sides X transpose AX bar, what am I getting? I'm simply getting this lambda bar X transpose X conjugate. This is again equals to what? This is again equals to X norm of X square lambda bar, and this negative take here. So what you are getting that your left hand side, this left hand side, which is equivalent to minus of X transpose AX, X transpose AX bar, it is equals to lambda X, you can say lambda X mod like norm of whole square. So I hope it is clear till now. Is that not clear or not? Is that clear or not clear? So I'll take a negative on both sides. So this is equal to minus lambda bar this thing. So your left hand side, I can write it as minus of lambda norm of X square, and here, see here what it is equal to. Here it is equals to what? The right hand side is equals to lambda norm of X square. So I would write it is equal to RHS. RHS is what? Lambda. This is, and I know that norm is always positive, as I have already written. That implies lambda, it is bar, it is equals to lambda plus lambda bar equal to 0. And if I write lambda plus lambda bar equal to 0, then lambda bar would be equals to what? It would be equals to minus of lambda plus lambda bar is equal to 0. That implies lambda bar would be equals to minus of a, minus of lambda. Now if I write my lambda is equal to, let's say, a plus iota b, let's say the eigenvalues are a plus iota b, so this will remain as a minus of iota b, and this will become minus of a minus of iota b, right? So this gets cancelled. It implies that 2a is equal to 0. It implies a is equal to 0. That implies either the roots will be purely imaginary, because if a is 0, then the roots are either purely imaginary or they can be 0. So always remember, for a skew symmetric matrix, the eigenvalues are purely real or are purely imaginary or 0. I hope it is clear. For Hermitian matrices, please remember the eigenvalues are always real. For skew symmetric matrix, please remember the eigenvalues are always purely imaginary or they are 0. I hope even if you have not followed the derivation part or proof part, you can skip this part, but remember this result. I hope it is clear. Please let me know in the comments. Are you getting it or you are not getting it? If you are not getting it, I'll repeat it all over again. Okay, so always remember, so we have already done these things. Okay, so we have already done these things, and please remember, here I have not stated here in this entire thing, I have not stated anything regards to the entries, So always remember, if this is the case, the same result applies to, I'll write it here, the same result applies to skew Hermitian matrices also. So we read yesterday that for Hermitian matrices, the eigenvalues are always real. For skew Hermitian matrices, eigenvalues are always as skew Hermitian matrices, the eigenvalues are always, what you can say, they're always purely imaginary or zero. Okay, for skew Hermitian matrix, we can extend this result that we have derived for your skew symmetric matrix. Okay, now you see, having said all these things, today we are going to start with the unitary matrices. But let us first do a few more things. One matrix I told you was involuntary, if you remember. If you remember, one of the matrix I told you was involuntary matrix. Involuntary matrix. Okay. Now, what is an involuntary matrix? If you remember, just use your notes. Just tell me what would be an involuntary matrix. Okay, what do you think that involuntary matrix would be? Okay, I told you that involuntary matrix is one where your A square is equals to I. Don't get confused with idempotent. A square is equal to A, then it is idempotent. But A square is equal to I, then it implies that it is implies that it is involuntary matrix. Involuntary matrix. If this is the case, then if this is the case, then remember it satisfies. I would say it satisfies the characteristic polynomial x square minus I, certainly, because if you remember, I told you that every matrix satisfies its characteristic polynomial. So if this was the polynomial, only then you can have this kind of matrix equation. Okay, so it implies that your eigenvalues would be either +1 or -1. So for involuntary matrices, please remember it would be either -1 or +1. The eigenvalues would be either +1 or -1. I hope it is clear. Now let us move to something called as unitary matrices. I mean, these are very important. And okay, let us also see something called as orthogonal matrices. Let us see something called as orthogonal matrices and a few examples of orthogonal matrices. So if you remember, we had done orthogonal matrices. And what are orthogonal matrices? Orthogonal matrices are one where your A transpose A is equals to A transpose is equals to identity. If you remember, your orthogonal matrices are one where your A transpose A is equals to A transpose, and it is equal to what? It is equals to identity. Those matrices are called as your orthogonal matrices, if you remember. Okay, so I'm just writing it here. A transpose is equals to A transpose A is equals to identity. Is that clear? Okay, so these are called as your orthonormal matrices. So I'm writing these are called as your orthogonal matrices. Orthogonal matrices. One of the important example of orthogonal matrix. Okay, one of the important properties, I'm going to write it here, and that is to think. I'll let you think over it. Just take a minute or so and think about it. That if a matrix is orthogonal, then its columns or even its rows. If a matrix is orthogonal, its rows or its column also form an orthonormal set. Always remember this. This is an important result. See, this is quite easy to see if you just take any example. Let us say that if A is my orthogonal matrix, then let's say A, B, C, D I'm writing, and what would be my A transpose? My A transpose would be A, B, and here it would be C and D. So if I do a A transpose, what am I going to get? I'm going to get A square plus. So if I just do A transpose, I'm going to get A square plus B square. Then I'm going to get AC plus BD. And what I'm going to get here? I'm going to get C square plus D square. Oh no. I'm going to get here AC plus. Sorry, I'm going to get CA plus DB here. and here I'm going to get c square plus d square, and it should be equals to what? If it is orthogonal, then it should be equals to identity. Now what does it imply? It implies what? It implies that a square plus b square equal to 1. I'm just showing you here. So it implies that a square plus b square equal to 1. Okay. It implies the it implies a normality condition. A normality condition for this row is specifically. Now think about this ACBD. What I can say, I can write it as A, B, C, D is equals to what? 0. So what is happening? If you take this this particular row A, B, and so if this is 1 and this is another column, if you take, let's say this is your column 1 and you say it is column 2 transpose, so what you're getting it as 0. So clearly you can see that the rows or columns form an orthonormal set. I hope it is clear. I hope it is clear. Always remember that your for orthogonal matrix, columns or rows also form an orthonormal set. If somebody is attending the lecture, kindly let me know if you are getting the point. Because it is orthogonal, na? So whether you say about columns or whether you say whether you say about rows or whether you say about columns. So a square plus b square means what? Your row or let's say your column is normalized, and if I multiply it with C2 transpose, so what it would be? A B C D, and then I can write this particular thing A as AC plus BD, and this is equals to 0. Is that clear? Good. So this is one of the important properties of orthogonal matrix. Now let us pay our attention to one of the very important class of matrices, which are referred to as the rotation matrices. These are referred to as the rotation matrices. When you're going to see the rotation, moment of inertia and rotation mechanics, there we are going to discuss like Euler rotations, and we are going to see different rotations in all the 3 directions, that is x, y, z. Today I'm going to just develop some results. Okay, today I'm going to just develop some results. So one of the matrix we have already seen while we were studying about orthogonal matrices definition. We have already discussed a rotation matrix of 2 cross 2. So I know that if I want to write a rotation in 2 cross 2, I can write it in this fashion. This is your rotation matrix. Cos theta minus sin theta, and here you will get sin theta, and here you will get minus of cos theta. Plus of cos theta. Okay. Now if you take a transpose, so this is your matrix, and I taught you that the eigenvalues for these matrices come out to be equals to e to the power plus minus iota theta. I'm leaving it for you. You just figure out. I have already taught you this. So eigenvalues of A is nothing but it is equals to e raised to power plus minus iota theta. Now for any real number, theta, where theta belongs to 0 to pi in 3 dimensions. If you remember that in 3 dimensions theta is restricted to 0 to pi. This particular for this particular thing, one of the rotational matrix can be defined as this. I'm just giving one of them. Cos theta minus sin theta, I can write it as 0, and then I will write it as sin theta here, cos theta simply here, and then you have 0, you have 1, 0, 0. This particular matrix A is also an orthogonal matrix. This is also an orthogonal matrix. So always remember these matrices, that is the rotation matrices, are orthogonal. So you can see that eigenvalues are e to the power plus minus iota theta, and if you take a transpose of it, you will get you simply get, I'm writing it here. So if you just take a transpose of it, A transpose into A, if you do, you will get an identity matrix. This is quite easy to see. For this you can see on your own. Here I'm showing it to you. Okay. So for this rotation matrix, if you just do A transpose, what would you get? You will simply get cos theta minus sin theta 0, sin theta cos theta 0, 0, 0, 1. And if you multiply it with like A itself, what you will get? I will write A transpose is what? It is equals to cos theta it is equal to sine theta here, it is equal to 0 here, minus sine theta here, then cos theta here, and then 0, 1 here, 0 and 0. And then you can write it as again this cos theta minus sine theta and 0, and here you have sine theta, here you have cos theta, here you have 0 and 0, 0, 1. Now if you just want to calculate this A transpose A, then what would you get? You will simply get, I think this would be, first I will write cos, so this will be equals to what? This will be equals to cos square theta plus sine square theta here, right? Minus minus plus, so it will be 0 here, it will be 0 here, so it will be sine square, sorry, it will be equals to what? First it would be minus cos theta, so it will be first 0, and then the second entry would be sine square theta plus cos square theta here. Here I think it would be simply 0, and then 0, 0, 0, here it would be 0, and here it would be simply 1. I know that sine square theta plus cos square theta is 1, so I can clearly write that A transpose A, and similarly I can verify it for A transpose. I'm leaving it to you for you to understand that A transpose A and A transpose is equals to identity. This particular matrix A is also an orthogonal matrix. Please remember, rotation matrix in 3 cross 3 is also A is also an orthogonal matrix. And I told you that for an orthogonal matrix, the corresponding row elements or column elements also form orthogonal set. So there is a bolder statement which suggests that a matrix is orthogonal. If you don't want to do this way, always you can write this way, that a matrix is orthogonal. A matrix is orthogonal if and only if its rows, a row or column vectors are orthogonal to each other. Are orthogonal to each other, or you can say they form an orthonormal set. Further, all the more bold, because as we saw early, that the row elements when behaved as if they are getting normalized, that is a square plus b square equal to 1, if you remember the previous one. So a matrix is orthogonal if and only if its row or column vectors form an orthonormal set. This is an important property that we have already listed. Just think about this particular scenario for this. So let us just think about this. So if I just take the column vectors here, I'm writing all the 3 column vectors so that you can see it on your own self, that the first column vector would be what? It would be cos theta. I think this was transpose now. So it would be cos theta, sine theta and 0. The second column vector I'm writing, it would be minus of sine theta, cos theta and 0. And the third column vector would be what? It would be equal to 0, 0 and 1. Now, if you want to clearly see one of the things, you can clearly see that if I take a norm of a1, so what would be the norm of a1? It would be equal to root over cos square theta plus sine square theta plus 1, and it is equal to 1. Okay, similarly norm of a2 would be equals to what? It would be equals to 1, and similarly norm of a3 would also be equals to 1. So all of them are normalized. Each of these column vectors are normalized. That is quite easy to see. And if I want to calculate, okay, and if I want to do this a1 dot a2, so if I do a1 dot a2, what I will get? So a1 dot a2 would be what? This would be cos theta, sine theta 0, and this is minus sine theta, cos theta 0. Okay, so if I do this way, what I'll get? Minus sine theta cos theta, minus cos theta sine theta plus sine theta cos theta plus 0. So I'll get a 0. Similarly, you can verify on your own self that if I am doing this, I'm taking a column vector I and I'm doing a dot product with j, what I'm getting chronicle delta ij. So this is a property which says that the column vectors are orthonormal to each other. For which matrix I'm saying this? For a matrix which is rotation matrix in 3 dimensions. So it is it forms an orthonormal set. It forms a orthonormal set. It forms an orthonormal set. So always remember, if a matrix is such, if you see that all the column vectors are getting orthonormal to each other, then you can clearly say that this particular matrix is an orthogonal matrix. Is that clear? I hope it is clear to you. If I want to find the eigenvalues for the same, So we have already found the eigenvalues for a 2 cross 2 rotation matrix. Today we are going to see for 3 cross 3. So if I want to see for 3 cross 3 what I am getting, so I'll do this cos theta minus lambda here, then I will write minus of sine theta here, then I will write 0 here, and this is equals to, here I will get sine theta here I will get cos theta minus lambda, here I have the 0, here I have 1 minus lambda, here it is 0, it is 0. So clearly if I expand about this, so I'll get 1 minus of lambda, and then inside I'll get cos square theta minus of 2 lambda cos theta, and so this is cos square theta plus lambda square and plus sine square theta, right? Plus sine square theta. So basically what you've got, I can write this particular thing as 1 minus of lambda times, this is I think lambda square minus 2 lambda cos theta, and then this is equal to plus 1 equal to 0, implies lambda is equal to 1 or lambda is equals to, if you calculate for this, this would be equals to what? It would be equals to 2 cos theta plus minus root over cos square theta minus 4 cos square theta minus 4. So this would be iota 2 iota sine theta divided by simply 2. So I'll get lambda is equal to e raised to power plus minus iota theta. So there are 3 eigenvalues. One is lambda equal to 1. Another one is lambda is equal to plus minus e to power iota theta. So what is very special about all these things? Both the eigenvalues for both of these things, for example, even for the 2-dimensional case, even for the 3-dimensional case, just remember that the eigenvalues modulus, the modulus of eigenvalues is coming out to be equals to 1. So modulus of eigenvalues for both for rotation matrices, I'm saying for rotation matrices, is equal to 1. That is quite easy to see. This is quite easy to see. I hope it is clear. Now, can it be generalized in general for orthogonal matrices? Can this be generalized for the orthogonal matrices? That is, for orthogonal matrices, the eigenvalues are always unimodular. This question arises: can this result be generalized for orthogonal matrices? So let us see. Let us see that whether we can generalize this for orthogonal matrices or not. So for an orthogonal matrix, let us consider that A is a n cross n orthogonal matrix. Let us say that this is a n cross n orthogonal matrix. Let us say this is a n cross n orthogonal matrix. Now, if this is the case, then what I would do, I'll simply write an eigenvalue equation, that is AV is equal to lambda V, and I'll take a norm on both sides. So what I'll do, I'll take a norm on both sides. And as you remember that if I want to take a norm of something, what I do, I take a conjugate of it, and then take a transpose, and then multiply with AB. So this is how you write your norm. Literally, when we will do inner product spaces, we'll do it in quite detail. But I know that if you're even a little bit of aware of quantum mechanics, this is something that you do quite often there. This is something that you do quite often there in order to find the normalization condition. Now, if you do this, so what would you get? So you would get, I can write it as V, conjugate transpose A, conjugate transpose. You know now this particular thing I can write it as V conjugate transpose A, conjugate transpose, and then I have this A and this V, and this is we are doing it for real orthogonal matrix. For real orthogonal matrix we're doing. So for real orthogonal matrix, if I write A bar, it is same as writing simply A. So what I would do, I can simply write it as V, this conjugate transpose, and I know that if A is orthogonal, then A transpose A would be identity, and here you have V. So eventually what you're getting, eventually I'm getting it is equivalent to V norm whole square. So the left hand side is V norm whole square. This is simply, it is V norm whole square, right? And what this would be, it would be equals to what? Lambda V, transpose into lambda V. And here it does not make sense for writing transpose here. So what you will get, you will simply get lambda mod whole square, and then you will get V norm whole square, right? Because this lambda is what? This is scalar, so there's no point of writing transpose of it. But conjugate, yes. So conjugate, I'm taking conjugate, lambda conjugate into lambda will give you lambda mod square, and V conjugate transpose into V, it will give you. And I know for the non-trivial cases, V would not be equal to what? 0. That is, it is not a 0 column vector. So what you are getting, you are simply getting that lambda mod whole square is equal to 1. What does it imply? It implies that your eigenvalues for orthogonal matrices are what? They are unimodular. Okay, so their modulus is unity. Is that clear? I hope it is clear. Everybody might have got what I want to convey. Okay, so now let us move to something called as what we have left as unitary matrices. So that will actually sum up our this particular eigenvalue discussion. So let us now concentrate on eigenvalue problem for unitary matrices. Okay, good. So I hope everybody's. I don't think there is something boring about it. I think you must be enjoying people. I don't know, but if there are certain glitches that I make, because actually at times what happens is I try to keep my lectures raw. Raw means I don't study much, so that I attempt all these things as if I'm a student. Okay, so that you should also remember that this is how things would be when you are doing some exam also. Okay, so let us discuss about eigenvalues for. Let us discuss eigenvalues for unitary matrices. So let us discuss an eigenvalue for unitary matrices. Okay. Now, earlier we were doing this orthogonal matrices where we are saying that A transpose A is equal to identity. Now, instead of A transpose, we will now say A dagger A. So for a unitary matrices, the difference is that instead of only transpose, we are also going to not only transpose, we are also going to take a conjugate of it. So basically, a unitary matrix U is one which satisfies this. U dagger is equals to U dagger U is equals to identity. So U dagger is equals to U dagger U is equals to identity. This is your what you can say unitary matrices. So basically, what is unitary matrices? What are orthogonal matrices? Orthogonal matrices are nothing but they are the special cases. The orthogonal matrix is nothing but it is a special case of unitary matrices. Okay, unitary matrices, all the entries may be complex also. If all the entries are real, then basically if all the entries of unitary matrices are real, basically then there is no point saying it unitary, then you can say them as your orthogonal matrix itself. The similar results follows here. The first result that follows is, as I told you in the above section, the first result is same, that every eigenvalue of a unitary matrix is of unit modulus. Second, the distinct rows or columns, the distinct when I'm saying distinct, then they're orthogonal. Otherwise, if I'm not writing distinct, then I can say orthonormal also. The distinct rows or column of a unitary matrix are orthogonal to each other. Are orthogonal to each other. I hope it is clear. So both of these results we have actually done in our you can say already in the orthogonal matrices. So the same results follow here. So I'm not going to derive all these things. I think this is quite easy to see. So therefore, is that clear? Okay. So these two results are same results. So I'm not going to prove them. They are analogous to what we have proved above. Okay, the same results. The same result. The distinct rows and columns of a unitary matrices are orthogonal to each other, and every eigenvalue of a unitary matrix is of unit modulus. I hope it is clear. So now let us let us summarize this here, and then we'll do a few questions. And let us summarize this. Let us summarize our understanding of let us summarize the eigenvalue problem for special matrices. So let us summarize this. So what I would do, I would make a I'll let you know what I'm going to do. So I'll make a unit circle, and then I think then it would be a helpful thing for you. Just give me a minute. Okay. So this is, I think, circle. So this is my circle. Okay. Okay. So what I will do, write it here. Okay, so this is your unit circle. This is your unit circle I'm writing. This circle represents a unit circle. So I'm writing it as a unit circle. Okay, just remember this is unit circle. Now, what did I tell you? Now let us come to our understanding. The first matrix that I taught you was idempotent. And if you remember, for idempotent matrix, the eigenvalues can either be equal to 0 or they can be equals to 1. So I'm writing it here. Eigenvalues can either be equals to 0 or equals to 1 for an idempotent matrix, if you remember. So I'm drawing it here so that you'll remember. Okay. This. Okay. Now you see. So this is 0, this is 1. So for idempotent matrix, I know that my eigenvalues can be either 0 or it can be either 1. Right? For nilpotent matrix, we found that all the eigenvalues are 0. So for nilpotent matrix, I can say that my all the eigenvalues are what? They are 0. Okay, now what do you think about orthogonal and unitary matrices? Just I taught you that orthogonal and unitary matrices, their eigenvalues will always lie on the unit circle. Basically, because if I say, let's say what is lambda is equal to 1, so it is 1 comma 0. What is lambda is equal to e ki power plus minus iota theta? So it will always lies on the unit circle. So let's say what I want to suggest is, let's say the eigenvalues were e ki power iota theta and e ki power minus iota theta. Don't you think that if I take a modulus of it, it would be equal to 1? So it represents mod z equal to 1, right? In general. So in general, I can say that the eigenvalues of I'm just trying to write it in one way so that you remember this particular thing, right? So you will not forget it. Otherwise, you will forget it somehow. So all the eigenvalues for you can say unitary and orthogonal matrices lie on the unit circle. So I'll write unitary or orthogonal here. Okay, where would your Hermitian matrix lie? So I told you whether it is a real Hermitian matrix or real symmetric matrix. The eigenvalues are purely real. So real symmetric matrix, whether I write or I write Hermitian, the eigenvalues are always real. Is that clear? What about involutory matrix? I told you for involutory matrices, the eigenvalues are either +1 or -1. For involutory matrices, eigenvalues are either +1 or -1. And now let us come to the point for skew Hermitian or skew symmetric. So for skew symmetric and or you can say skew real symmetric and skew Hermitian, the eigenvalues are either 0, which will lie here only, or purely imaginary. I hope it is clear till now. Okay, so just let me know if there is any doubt. So we'll now proceed for the questions. Okay, so I have summed up our entire lecture, I think 2 days lecture in this particular one diagram. Okay, so please remember this particular diagram, and then most possibly it will give you a lot much of insight. So each of the eigenvalues I have presented here. Okay, now let us do a few questions. Let us do a few questions and then we'll go ahead. Let us do a few questions and then we'll go ahead to one of the very important aspects of matrices, which is similarity and diagonalization. But before that, let us do some questions. And now I'll wait for your responses. So kindly be responsive. Kindly be responsive. Okay. Now, the first question, it's quite easy. Okay. So we have done a good amount of questions on eigenvalues, eigenvectors. Now a little bit of more questions so that you just get a good hand at it, and then we'll see. Okay, just give me a minute. I think I missed the question somewhere. Just give me a minute. Okay, the question is find the values of alpha. Find the values of alpha such that matrix this that I'm giving to you 3 alpha, alpha and 5 has 2 as an eigenvalue. We have to find those values of alpha such that 2 comes as an eigenvalue. So one of the eigenvalues is 2. So one of the eigenvalues is 2. How to think about this? So it says that there is a matrix 3 alpha, alpha and 5. Okay. Now what has been asked to us? It has been asked to us that one of the eigenvalues is 2. So this is a 2 cross 2 matrix. Another eigenvalue would be what? So let us say that other eigenvalue is lambda. So let lambda be the other eigenvalue except 2, apart from 2. Okay. So this is one. Now if you remember, if I have a quadratic equation, I can construct it in this form: x square minus sum of roots times x plus product of roots. Okay. So if I want to write, I know if I want to write the characteristic equation would be what? Characteristic equation would be simply x square minus sum, which is equal to lambda plus 2 times x, and here I will get plus 2 into lambda, right? And I know that trace this particular thing is given as trace, so I can say that my lambda plus 2 would be equals to what? Trace is what? 8. So it implies lambda would be equals to 6. So other eigenvalue would be other eigenvalue would be simply lambda is equal to 6. So other eigenvalue is lambda is equal to 6. Is that clear? And what is the product of eigenvalues? So one is 6, another is 2. So product of eigenvalue is 12. And what it is equal to? It is equal to 15 minus of alpha square. So what does it imply? It implies that alpha square would be equals to what? 3. It implies alpha would be equals to plus minus of root 3. So answer is that if one of the eigenvalues is 2, then the alpha for this particular matrix 3 alpha alpha 5 can be either plus root 3 or minus root 3. Okay. Now let us write down another question and try to solve it. The question is what is the condition on A, B, C and D for the matrix A, B, C, D such that it does not have an eigen such that it does not have a real eigenvalue. So what do you think should be a condition on A, B, C, D such that this particular matrix A, B, C, D does not have a real eigenvalue? Just think about it. I'm giving you a minute or so, and then we'll solve it. I hope it is clear. The question is clear to you. Now let us start with the answer. So I think everybody has read the question. Now let us start with the answer. So the answer would be, I have already stated that this is a matrix, and we want to find conditions such that it does not have a real eigenvalue. Okay, it does not have a real eigenvalue. And I told you in the just before question that if I want to write a characteristic equation for the same, it would be x square minus trace of a. So let us say this is equals to a, trace of a into x plus determinant of a equal to 0. So this is how you can write. Okay, this is how I can write. Now I already know what is trace of a. So trace of a is I think a plus d, and here you have x, and then what is a determinant of a? Determinant of a is simply a d minus bc equals to 0, right? Now, if it does not have a real eigenvalue, that it implies that discriminant to this particular equation should be less than 0. The discriminant for this particular equation should be less than 0. And if I want to find the discriminant, it is equals to a plus d whole square minus 4ad minus bc must be equal to 0. So this is the condition by which I can say that my eigenvalues to this particular matrix will not be real. I hope it is clear. Because after all, eigenvalues can only be found by the Cayley-Hamilton equation, right? This characteristic equation. And if I'm saying that the roots for the characteristic equation are are imaginary, it implies that discriminant corresponding to it should be less than 0. Okay, one notation I'm showing you. Although when we are going to move into linear algebra, then it would be very sound notation, and you will be doing this. I'll be using it quite frequently. Let A belongs to a set of matrices, 2 cross 2 matrices with real entries. It implies set of 2 cross 2 matrices with real entries. So let A be a matrix which belongs to set of 2 cross 2 matrix with real entries, such that the eigenvalues to A are either +1 or -1. Eigenvalues to A are either +1 and -1. Then which of the following statement is true? Which of the following statement is true? A inverse is equal to A. B. A inverse is equal to -A. C. Both. D. None. So what do you think? Which of the statement is true? So A inverse is equal to A inverse is equal to -A, both or none. This is what it is. It is being said. So you see, I have already stated that eigenvalues are ±1. So if eigenvalues are ±1, what do you think the characteristic polynomial could be? Just think about it in reverse. So if I want to write the characteristic polynomial, so here it is. If I want to write the characteristic polynomial, for A, what it would be? It would be equals to x square minus 1, right? Only then you can have this plus minus 1, right? If it is the case, then I know that characteristic polynomial is satisfied by the matrix itself, so I can write a square minus identity is equal to 0. It implies what? It implies a square is equal to identity. And if I pre-multiply both sides by, or post-multiply both sides by a inverse, what would I get? I'll get a is equal to a inverse. So clearly, option number 1 would be the correct answer. Good. So people are getting answers. That is good. That is very good. So now let us do a few more questions, and then we'll move ahead. Okay. So I think these questions are beneficial, or you're not getting, or you're getting. Please let me know. Okay. So now let A be a matrix which belongs to set of real matrices, set of 2 cross 2 matrices with real entries, such that trace A is equal to 2 and determinant A is equals to 3. We have to write the characteristic polynomial of A inverse. Try to write the characteristic polynomial of A inverse. Try to write the characteristic polynomial of A inverse. See, I already know what? I already know that trace A is 2, determinant A is 3. So the characteristic polynomial to A would be x square minus 2x plus 3. So this would be a characteristic polynomial of A. This would be characteristic polynomial of A. So I know that every matrix satisfies its own characteristic polynomial. So I can write A square minus 2A plus 3 is equal to 0. Okay, now if I multiply this entire side by a raised to power minus 2, I'll get identity here. I'll get minus 2a inverse here, and here I'll get 3a minus 2 is equal to 0. What does it imply? It implies that if I want to write it as a minus 2 minus 2 upon 3 A inverse plus identity equal to 0, does it not mean that A inverse is satisfying a characteristic polynomial of x square minus of 2 upon 3x plus 1 equal to 0? So this would be your characteristic polynomial of A inverse. This would be your characteristic polynomial of A inverse. So this is your characteristic polynomial of A inverse. Is that clear? I hope these questions are quite clear to you. A few of them you should practice, and just one more, and then I'll do a few more things relevant to this only. One thing I have missed, so I'll teach you that also, so that you are not able to then you will not be confused at all. So just give me a minute. So question says that let A be a 3 cross 3 matrix with complex entries. Whose eigenvalues are whose eigenvalues are 1 iota and minus 2 iota. 1 iota and minus 2 iota. If A inverse is given as A times capital A square plus B times capital A plus C times identity, where ABC belongs to complex, then what are the values for ABC? You have to determine the values of ABC. What are ABC? What do you think ABC would be? Okay, what do you think the answer would be? So I already know that my eigenvalues are, okay, I already know that my eigenvalues are uh, 1 iota and minus 2 iota. I already know that my eigenvalues are this. So if you remember a little bit of your cubic equations, then it is quite easy to see. So I'm giving you a hint. Try to write a cubic equation for the same, and once you write a cubic equation, you will be able to understand the remaining things. So just a hint that you try to use cubic equations, because see, here you have 3 entries, now 3 cross 3. So what you'd get a cubic equation, right? Think about it. It's not that difficult. And still you are not getting it, then I'll do it for you. Don't worry. Okay, so if you're not getting it, I'll solve it for you. So for a cubic equation, so let's say if I'm writing a cubic equation ax cube plus bx square plus cx plus d equal to 0, then what I can do, let us say it has three roots. Let us say it has three roots, alpha, beta, and gamma. If it has three roots, then always remember that alpha plus beta plus gamma, here it is given by minus of b upon a. What is c then? Then it is equals to alpha beta plus beta gamma plus gamma delta gamma alpha is equals to what? It is equal to c by a. And what is alpha, beta, and gamma? It is equals to minus of d upon a. Okay, so this is how you write the different you can say the roots, and I can relate these roots like alpha plus beta plus gamma is minus b by alpha beta plus beta gamma plus gamma delta gamma alpha is equal to c by a, and alpha into beta into gamma is equal to minus of d upon a. And I know that already alpha, beta, gamma are supplied to me. So what would be minus b upon a here? So minus b upon a would be 1 plus iota minus 2 iota. So this is simply 1 minus iota, right? What would be alpha, beta, beta, gamma plus gamma alpha? I think it would be iota. And then this would be minus plus 2. And this would be minus of 2 iota. So this is alpha, beta. This is beta gamma, and it is gamma alpha. So this is what I have written here. So if I write it this way, I will get 2 minus of iota, right? So my 2 minus iota is nothing but it is equal to c by a. And then what would be this alpha beta gamma? So alpha beta gamma would be simply 2. If you remember, 2 iota is 2 minus 2 iota, and iota, this is minus 2 iota square, which is minus 2. So alpha beta gamma is simply this this thing which is equals to d upon a, right? I hope it is clear. Okay, now for convenience, if we choose the first a as 1, so what I'll get? I'll simply get my x cube, and this particular, if I divide it by a throughout, so b by a is equal to what? It is equal to 1 minus b by a is equal to 1 minus iota. If I'm dividing by a, so I'm getting b by a here, 1 minus iota x square. And then c by a, what would be c by a? C by a is, I think, 2 minus iota. And then 2 is this. I'm so sorry. This particular thing is the characteristic equation. Now this particular characteristic equation is satisfied by the polynomial itself, right? So I'll write this characteristic equation also satisfies the the matrix also satisfies this characteristic equation. So I'll write a cube minus 1 minus iota a square plus 2 minus iota, oh I forgot x here, so a and minus 2 times identity is equal to 0, right? And now I want to write what? Now I want to write my a inverse. What would be my a inverse? I have to multiply throughout by a inverse, take this to there, so I'll get a inverse is equals to 1 upon 2 a square minus 1 minus iota upon 2 a plus 2 minus iota upon 2 times identity. Now I think it is quite easy to see what would be your a, b, c. So you just compare these two things. C would be equals to this 2 minus iota upon 2. A would be equals to what? A would be equals to 1 upon 2, and B would be equals to minus minus. So this would be iota minus 1 upon 2. So B would be iota minus 1 upon 2. I hope you've got the answer to this particular question, and I don't think there is an issue. So we have studied till now rotation matrix. Now let us do one special, that's not even special matrix, but let us write some results regarding reflection of matrices. Reflection of coordinates which can be represented in form of matrices. Some important results I'm going to write. Okay, I'm not going to derive them because of the lack of the time. probably not today, but then tomorrow we are going to start with diagonalizability. But overall, please remember this reflection matrix. Okay, so this is reflection matrix, and now let us take the case one. So uh, okay, so let me explain you a few of them. I'll explain, and then one of the general result I'm going to write it directly. Okay, so these all things are not that difficult for you to have, but still I'm writing. So let's say reflection in the x-axis. So if I want to write a matrix which represents a reflection in the x-axis, how would I do it? So let us say this is my matrix. These are my points. So let's say this is my point x comma y. So if I want to do a reflection about x-axis, so I'll get this point here, which is p dash, which is simply x dash comma y dash. And I know that for this particular thing, my x dash would be simply equals to x, but my y dash would be simply equals to minus of y. You're getting my point? If I do a reflection about x-axis, my x dash would be x and my y dash would be minus y. And if I want to write this in terms of matrix x dash y dash, I can write this x as, I think, 1 into x plus 0 into y, and I can write this as 0 into x and plus minus y minus 1 into y. So I can write this as 1 0 0 minus 1, and then this is simply x and y. Okay, so this is your reflection matrix. So if I want to express my reflection taking x-axis as a image, taking x-axis as the mirror, then that particular reflection matrix I'm writing it. So this particular reflection matrix along is given by 1 0 0 minus 1. So this represents what? It represents reflection of point x comma y, reflection of x comma y in the x-axis. I hope it is clear till now. Okay, now let us move to reflection along y-axis. If I want to write reflection along y-axis, how would I do so? So all these things you can even do in exam also. Okay, if your exam is there. So let us say this is your let's say this is your point P, which is x comma y, and if I want to write the reflection, so here it would be a reflection along y-axis, and let's say this is my point P dash, and it would be x dash comma y dash, and I can say that my x dash would be simply minus of x, but my y dash would be simply y. And so if I want to write this stuff up, I can write x dash y dash is equals to minus 1 0 0 1, and here you have x comma y. So always remember, this particular matrix represents the reflection of point, it represents reflection of point x comma y by about y-axis. Okay, this particular matrix minus 1 0 0 1 represents reflection of x comma y about y-axis. Okay, now next, reflection about origin. What is reflect? What do I mean when I say reflection about origin? Let's say this is my coordinate system. Let us say this is the point x comma y here, and if on origin, if I take an image, and let's say this is another point, this would be minus x and minus y. This would be an image. So this is P, then this would be what? This would be P dash. So what I can write, I can simply write that my x dash would be minus x and y dash would be minus of y. So in general, I can write that x dash y dash is equals to minus 1 0 and 0 minus 1 times xy. So this particular matrix represents reflection about origin. It represents reflection about origin. This particular matrix represents the reflection about origin. Minus 1 0 0 minus 1. I hope it is clear till now. Now if I want to write reflection about y is equal to x, so if I want to write reflection about y is equal to x, then how to go about it? So I'll do this thing. I'll make a line here. This is simply y is equal to x. If I'm writing a point here which is p x comma y, and how do we represent the distance? Distance are always perpendicular. So this is how your p dash would be. This is how your p dash would be. This is how your p dash would be. And let us write it as x dash y dash simply. So when you take a reflection here, what happens is, okay, so let us say this is your o dash. Okay, so let's say this is your o dash, this is x, and this particular thing is x dash comma y dash. Okay, now if you take this kind of if you do this kind of stuff, so what is happening? So what should I do? So let's say okay, so what should I write about o dash? So what can I write about o dash? I can write that so this is y equal to x. So this okay, this line is y equal to x. This line is simply y is equal to x. Okay, this line is simply y is equal to x, and okay, so I'm writing down the points right now, just that I remember that x dash is replaced by y, okay, and y dash is replaced by x. Okay, this is something that I'm giving you as a homework. Try to do it. I will guide you once you get it. You just use this property that o dash is what? O dash is your, sorry, o is what? O is your midpoint. Just use the property that your o is a midpoint, nothing else. Everything else would be quite easy to see. Since o is midpoint, then you know that x plus x dash by 2 can be written as the coordinates of u. Okay, so x plus x dash divided by 2, you can write it as the coordinate of o. Is that clear or not clear? So if you do this way, so what I'll get, I'll simply write x dash y dash is equals to, I think it would be 0, it would be 1 here, it would be 1 here, it would be 0 here, and it would be x and y. So when it comes to reflection about y is equal to x, what you can do, this particular matrix, identity 1, it represents what? It represents the reflection about, the line y equal to x of the point x comma y. I hope it is clear. Okay. I hope it is clear till now. Okay, so this represents your reflection about y is equal to x line. So if you are going to see that the reflection particular transformation about line y equal to x is represented by the identity matrix. This is something that you should understand. Okay, and I'm leaving it to you as a homework to find that x dash is y is equal to y it is equal to y, and y dash y it is equal to x. I have given you the hint. Then try to use the bisector formula. Try to use the bisector formula, and then you will be able to get it. It's not that difficult. Just think about it and you will get it. Okay, now instead if somebody says that y is equal to mx plus c, if that is the line, then it is slightly tricky, and I would directly write you the formula so that it does not waste your time as such. So I'll directly write the formula here. So instead of this, if I am telling you to write a reflection about any general line, y is equal to mx, and m is given by what? M is given by tan theta. So if you want to write reflection, I'm directly writing the result, don't worry, because this involves a coordinate geometry in which I'm right now not very keen in. So reflection about the line y is equal to x tan theta. Line y is equal to x tan theta. So if there is another line, let's say this is your line, and this is theta, so this is y is equal to x tan theta. And if you have a point P here, this is x comma y, and if you have a point P here, which is x dash comma y dash, and if I want to write the if I want to write the x dash y dash, then x dash y dash can be written as, it is given by cos 2 theta here. Here you will get sine 2 theta. Here you will get sine 2 theta, and here you will get minus cos 2 theta. Okay, and then you get x and y. I'm just telling you, don't worry about all these things, because this will involve a little bit amount of coordinate geometry, which right now I'm not keen at. So please remember these results. Please remember these results, at least two of them. I think this one is quite easy to see, that x dash would be equal to y and y dash would be equal to x. This is the reflection about y is equal to x. So it is the reflection about y is equal to x. If I do a reflection about y is equal to x, my x dash would become y and my y dash would become x. Okay, and I can say that the identity matrix represents the reflection transformation about y is equal to x. Similarly, if I have this y is equal to x tan theta, then the reflection matrix is given by cos theta, sine 2 theta, sine 2 theta, minus cos 2 theta, sorry. It is minus cos 2 theta. Okay, I hope you've got this particular point. Okay, now just think about this. Just think about one of the things that I'm trying to tell. If you're not getting these results, I'll prove them tomorrow. Don't worry, I'll prove them tomorrow. Okay, I'll prove them tomorrow. Right now, I'm not getting the right way of doing these things, but I'll prove it tomorrow. If these are your homeworks, if you're not trying, if you try it and you're not able to get it, then we'll do it. We'll do it tomorrow. Okay, but before we go tomorrow, let us do one more thing. Let us do one more thing, which is actually, let's say if I have got one matrix which represents rotation through angle theta 1. What is a rotation matrix? Rotation matrix is simply cos theta 1. Here you would get minus sin theta 1. Here you have this, here you have this minus sin theta 1. Here, I think here you have sin theta 1. And here on the fourth side, this here you have cos theta, right? This is how you represent your rotation through angle theta 1. If you have to represent your rotation through angle theta 2, what you will get? You will simply get cos theta 2. I will write minus sin theta 2, and here you have the sin theta 2, and here you have cos theta 2. Now if I tell you to multiply this a theta 1 into a theta 2, what you are going to get? You are simply going to get, I think it would be cos theta 1 cos theta 2 minus sin theta 1 sin theta 2, right? And if I do this, I'll get minus of cos theta 1 sin theta 2 plus, again minus, and I don't have to write this way, otherwise you'll get confused. Okay. So if I'm saying that I have two rotations, so one rotation is given by theta 1 angle, so it will be cos theta 1 minus sin theta 1 sin theta 1 cos theta 1, right? And another rotation is through angle theta 2. Another rotation is through angle theta 2. And if I want to multiply both of them, what I'm going to get? Just think about it. Meanwhile, I'll get this eraser somehow. Okay. Just think about it. What you will get? Okay, I'm writing it here. So multiply these a theta 1 and a theta 2. Multiply these a theta 1 and a theta 2. What you're going to get? You're going to get cos theta 1 cos theta 2 minus sin theta 1 minus sin theta 2, which is equals to cos theta 1 plus theta 2. Okay. If you take this and this, then it will be minus cos theta 1 sin theta 2 plus minus sin theta 1 cos theta 2. So you will get minus of sin theta 1 plus sin theta 2. If you take this, then you will get sin theta 1 cos theta 2 plus cos theta 1 sin theta 2, which is equals to sin theta 1 plus theta 2. And the last one you would get, I think it would be cos theta 1 plus cos theta 2. So when these matrices are multiplied, the arguments are additive here. Similarly, if you multiply this n times this particular matrix, then you will get what? You will get a n theta. Are you getting my point? So if a matrix which represents rotation through angle theta, if it is multiplied n times, you would get a matrix where the argument like theta get replaced by n theta. Are you getting my point, or are you not getting my point? And remember, these are orthogonal matrices. If that is clear, then I should move ahead, and if that is not clear, I will repeat the point. Please let me know if there is an issue. Okay, and the reflection matrix one, that would involve coordinate geometry. Right now, I'm not aware of the proof, whatever I think is that most possibly, it's an easy mathematics, easy coordinate geometry. You just take a reflection about y equal to x, then O is the midpoint. Try to utilize that. If you're not able to utilize that, then I'll be willingly helping you tomorrow, because today I want to focus on a few more things. Okay, so this is your rotation matrix when it is let's say multiplied n times. So if I'm doing an, if the rotation matrix is there, and if I'm multiplying it n times, then instead of theta, the theta would change to n theta. The argument would change to n theta. Is that clear or not clear? So I'll give you a question. To make you understand what I'm trying to say. Okay, so one of the question that I want to give is this, so that you are able to understand what I want and why I'm doing this for you. So for example, I'm giving you a question. It's a simple question. Which of the following matrix, which of the following matrix satisfy that a raised to power 6 is equal to identity? A raised to power 6 is equal to identity. Okay, and let's say this is the first matrix A, and it is given by cos pi by 4, sin pi by 4 0, and then you have minus sin pi by 4, then you have cos pi by 4. Option number B, A is given by 1 0 0 and then 0 cos pi by 3, sin pi by 3, and then 0 minus sin pi by 3, and you have this cos pi by 3. Okay, then C, option number C is what? It is given as A is equal to cos pi by 6, 0 sin pi by 6, and here you have 0 1 0, and the last entry is minus sin pi by 6, 0 cos pi by 6. And option number D is what? Option number D is simply A is equal to cos pi by 2, then you have the sin pi by 2, then you have 0, and then you have minus sin pi by 2, and then you have cos pi by 2, then you have a 0, then 0 0 1. What do you think A raised to power 6 is equal to identity? Which of the following matrix would satisfy this property? I am giving you a minute to think about it, and if you are not able to do it, then I'll do it for you. Okay, so I'll do it for you. So remember, I taught you these rotation matrices. That rotation matrices are nothing but they are orthogonal matrices. Now, most generally, the rotation matrices are represented by Rx theta, that is rotation along x-axis, and that is like 1. I think it is 1 0 0. If I remember that. Okay, so it is, I think, 1 0 0, and then you have this 0 cos theta minus sin theta, and then you have the 0, and then you have the sin theta, and these are all we are going to study in rotation mechanics also, don't worry. Another way of representing it along a different direction is writing it in this form: cos theta 0 sin theta 0 1 0, and then you have minus sin theta, and then you have the 0, and then you have this cos theta. And if you remember, one of them we have done today morning itself. This is this representation we have done in the morning itself, that is cos theta. Here you had minus of sin theta. Here you had 0. Here you had sin theta. Then you had cos of theta. Then 0. This was 1, 0, and 0. So going by these, all the above matrices, all the above matrices are nothing but rotational matrices. So all the above matrices are nothing but rotation matrices, right? And I taught you one property of rotation matrix, that if there is a rotation matrix which is let's say represents a rotation through angle theta, and if I raise to power n, then it gets a n theta. Now you have to identify which of the following gives you the answers. For example, it is given a6 is equal to identity. It implies that if you replace your theta by 6 theta, which of the following matrix will give you an identity matrix? Now just think about it. If you replace theta by 6 theta, so here if it is replaced, let's say here if I replace, let's say this is your theta here, this is your theta here, just think about it, this is your theta, so your theta is equal to what? It is equal to pi upon 3. Now if I replace it by 6 theta, what I'll get? 1 0 0 0 cos 6 theta means cos 2 pi, it would be 1. Here it will be sine 6 pi by 3, which is sine 2 pi, which is equal to 0. Here we will get 1, here we will get minus 0 0. So if I do a raised power 6 for this particular matrix, what I will get? I will get a6 theta, and certainly a6 theta would be equals to what? It would be equals to 1 0 0 0 1 0 and 0 minus 0, which is simply 0, and then 1. So what am I getting? I'm getting an identity matrix. So please remember, this would be an answer to this. I hope now it is clear to you why I was emphasizing on this point. Although I have not given you a proper proof, but I have just tried to relate it somehow, so that you can manage things on your own from here. I hope it is clear. Okay, now let us move to one more question, and then if time allows, then we'll start with diagonalization. Otherwise, diagonalization we'll do tomorrow. So good. Okay, so one more question I'm going to give you, and I hope that is easy for you to understand. What should I write? I will write consider the matrix A is equal to cos of theta, sine of theta, and then you have this minus of sine theta, and then you have this cos of theta. Okay, just give me a minute. Okay, just give me a minute. I'll make a question for you so that you'll feel interesting thing about it. So let's say your exam is in 2024, right? So your exam is in 2024. Just give me a minute. Okay. Okay, and let us say okay, so let us say that theta is given by 2 pi divided by let us say 44. Let us say 44. Okay, then what do you think would be a raised to power 2024? Okay, your exam is in 2024 now, so this is a question. Okay, so consider a matrix which is given by A is equal to cos theta sin theta minus sin theta cos theta, and your theta is given by 2 pi upon 44, and then I want you to write what would be the values, what would be the value of a raised to power 2024. Don't worry about it. I know that my A is a rotation matrix, right? I know that A is a rotation matrix. And since A is a rotation matrix, what I can do, I can write that my A theta raised to power 2024 would be simply A 2024 theta, right? This is how I can write. I already know that my theta is equal to what? 2 pi upon 44. And just remember, 2024 divided by 44 is nothing but it is equal to 46. Okay, so this is what I was calculating. So 2024 divided by 44 is 46. So what I would do is, if I write it here, cos 2024 theta. So cos 2420 theta would be equals to what? So it would be equals to cos of 2 pi divided by 44 into 2024 theta. Sorry, instead of theta I have already stated 2 pi upon 44, and then it would be sine of 46 pi. If you remember, this particular ratio is 46 is 92 pi, and here you will get minus of sine of 92 pi, and here you will get cos of 92 pi. So what we will get, cos even multiple is 1, cos even multiple is 1, and even multiple of pi, and if you apply sine to it, this will be 0, so you get an identity here. So I hope such questions, if they are asked in your examination, I hope you will be able to do them. Is that clear or not clear? Please let me know on the comment section if that is clear. I hope these questions are not that difficult for you. Okay, that's good. Okay, so now let us do a few more questions based on such things. Then probably regulation will do tomorrow. Okay. Okay. So just think about this. Just think about this. So we have done reflection matrices, we have done rotation matrices. Now I'm giving you a simple question, and then let us think, will you be able to do it or not? So question says, it is from just examination. It is from just examination. And see what it says. It says that there is a coordinate transformation given by x dash is equal to 0.8x, okay, plus 0.6x y, and then you have this y dash is equal to 0.6x, and then you have this minus 0.8y. This particular transformation represents one translation. Does it represent a proper rotation? Does it represent a reflection? Or does it represent D, none of the above? What does it represent? What do you think the answer would be? I'm giving you a minute to think about it, and then I'll do it for you. Okay, what do you think it would be? Would it be a rotation? Would it be translation? Would it be reflection? Or would it be none of the above? Just think about it and then answer. So I mentioned that if you are having okay, so I mentioned that if you are having a reflection, I mentioned few cases. Okay, I mentioned few of the cases, and using those cases only, you can think about this particular matrix. Using those cases only, you can think about those matrices. Okay, so clearly remember that I told you that a rotation is represented by uh, you can say an orthogonal matrix. Now here I'm writing x dash y dash, and here I'm writing 0.8 here. Here I'm writing 0.6 here. Here I'm writing 0.6, and here I'm writing minus 0.8. And remember, here you have this x and y. Now just try to think. That when I taught you, sorry. Okay. So when I taught you that if I am going to make a reflection about line y is equals to x of tan theta, then certainly you had these entries being written in terms of cos 2 theta, sin 2 theta, and so on and so forth, right? And so if you apply that concept, then you will be able to judge it very clearly. So if you remember, just remember, I'm writing it here. Just remember, okay. So just remember that if I wanted to write the reflection matrix in general for theta, so what it was clearly equal to, if you remember, it was cos 2 theta here, it was sin 2 theta here, it was I think sin 2 theta here, and it was minus cos 2 theta here, right? And clearly if your cos 2 theta is 0.8 then sin 2 theta would be 0.6. That is quite easy to see that if I take my cos 2 theta as 0.8, then my sin theta would be equals to what? 1 minus of 0.8 ka whole square, and it would be certainly 0.6. So if this is your 0.8, this would be your 0.6, it would be 0.6 here and it would be minus 0.8 here. So clearly, and also remember, whenever you are taking a reflection matrix for any arbitrary angle, if you are trying to write reflection matrix for any arbitrary angle, it is quite easy to confirm. For other also you can confirm, or you know that the determinant is equals to 1. So the determinant is equals to what? Oh, sorry, determinant is equals to minus 1. So clearly you can verify here, minus 0.8 into 0.8 minus 0.64, and here it is minus 0.36. So clearly this determinant is equal to minus 1. Here also you can compare the two, and you can clearly see that this is reflection about line y is equals to x tan theta. It is clearly reflection about line y is equal to x tan theta, where theta is given by what? It is very easy to see that your theta would be, if I write it as sin 2 theta divided by cos 2 theta, which is simply tan 2 theta, which is equals to what? Which is equals to 0.6 divided by 0.8, and that is equals to 3 over 4. So it is clearly reflection about line y is equal to x tan theta, with theta given by half of tan inverse of 3 upon 4. Okay, I don't know exactly where tan inverse 3 by 4 would be, but in general I can write this. So it represents what? It represents a reflection in particularly about line y is equal to x tan theta, where theta is given by half of tan inverse of 3 over 4. I hope this particular lecture has given you some insight on the questions of matrices. This particular question was asked in test examination. I'm going to do much questions tomorrow, and then we're going to start with something called as diagonalization, which is quite important for your physics. Okay, so that will be the end of your matrix algebra, probably 1 or 2 lecture more, and then we shall start with linear algebra on one side, and on another side we'll start with the quantum mechanics. I hope to meet you tomorrow. Till then, take care. Bye bye. Happy Independence Day to all.